טכניות. We will most likely need to add up the extra lectures. So what I need from you, I made a small table, and you write down, you mark whenever you cannot add lectures. If there's X when you cannot, so mark down the lectures and where it's impossible. So we'll see whatever open slots are left after everybody will fill in whatever you cannot have extra lectures. So please.
There? No. No? בוא נראה אם נתקעו פה משהו. למה זה מסודר? אני מסודר. מה אתה עושה? לא אל תיגע.
לא, סתם בדקתי רואים את המצלמה.
שבי?
לא רואים.
להיות ככה. אז הם מתנגד.
אתה שואל כאילו על שעה שבועית שנעשה שיעורי השנה או פשוט לשבוע הבא?
רגע, כן. לא, שבועית באופן כללי. נראה, כי כל הסמסטר הזה מאוד וייג כרגע. מה היה המצב? אני צריך להבין, אבל אני בכוונה רוצה להערך לזה עכשיו כמה שיותר מוקדם. כמובן שלפני שיעורי שעות אקסטרה תהיה הודעה מסודרת לכולם. כמובן צריך להבין מתי אפשר ומתי אי אפשר. שבוע הבא כרגע יש מועד היבט, אין לימודים.
שבוע הבא אין לימודים?
באופן עקרוני כרגע האוניברסיטה הודיעה ששבוע הבא...
אני מספק אם נצליח להגיע אפילו לחמישי.
זה לא תלוי באף אחד מאיתנו.
שבוע הבא אין?
ההודעות הרשמיות של האוניברסיטה, אני מקבל אותן בדיוק כמוכם, אני לא יודע ואני לא שואל לי שום שליטה על זה. אומרות שהשבוע הזה יש לימודים כרגיל.
לא, היה משהו שהם הודיעו שהם יעשו אחרי המלחמה, שהם יעשו שבוע מרוכז של כל המבחנים
זה יוצא מיום חמישי הקרוב, ביום חמישי הקרוב, השבוע הקרוב יש לימודים כרגיל. ויש גם מבחנים בשבוע הבא. אנחנו יכולים להתחיל, אורן.
טוב,
מה עושים?
ביוטיוב רואים דירקשן.
רגע, אז מה זה? זה לא המצלמה.
זזות, הצדדית, אין לי מושג איך. אתה רואה? אם זה כל כך... לא רואים.
מוזר.
רואים מה זה המצלמה.
זה כן, זה בטח שזה המצלמה. זה מזיז אותה.
גם סגור בסיטוציה בששנה.
בסדר, מה קורה?
כן, זה זה.
עכשיו זום אאוט.
כן, אבל עוד מה? עוד שעה, תקשר עוד שעה.
אנחנו רוצים לתת הרצאה.
היי, אסף? זה כותב שיש מועד גרעינית ביום רביעי.
כן,
זה לא אפשרי.
לא.
זה לא-
חברים, בכל מה שנוגע לבחינות,
קצת תפסת אותי
מול מדור
באמצע
בחינות, זה
בזמן
לא קשור
לא
אליי.
טוב. כן.
אני לא יודע מי הזיז, מתי הזיזו,
ביי.
אין לי שום מושג. תוודאו את זה מול מדור בחינות.
בעיקרון עומדים בשם
לא נראה לי שזה יהיה.
זה למה זה מסתדר.
טוב, אבל ננסה. זה לא.
אי אפשר לעשות את זה.
זה בעיקרון, לא יודע,
פיזית
אם
שם
יש,
לא.
היום
קודם מה
מחר.
אין מושג. לא יודע.
יש שלט אצל מירי. כן. שלט של המצלמה, כתוב עליה אבר. אתה יכול להתחיל פשוט, אתה יודע, תסתכל איך רואים.
אתה לא יכול לעשות זום אאוט?
אמרתי לו, צריך עם שלט.
טוב, אני מציע שנתחיל We should start because otherwise we're losing too much time.
I think in worst case scenario, you could probably reference people to the recordings from previous years to see a fairly similar lecture.
Well, in principle, everybody should be here. Right? Of course, except those, there are some people that may not be able to be here at the moment because of the army or because they're stuck somewhere. But, yeah.
Lectures recorded?
The lectures, as I sent you, I don't know if you've seen, I sent a message to all the entire students of this course. Right now, all the lectures are recorded. And they would be, I'll try to add them. This is not via my personal Zoom, but via the university link which is attached to this machine somehow. Okay, so let's do a quick recap on where we've been and where we're heading. So before the Passover holiday, we completed the discussion about special relativity. I'm not going to repeat everything here. I'll give you my lecture notes and I strongly advise you to go and have a look. And the one thing that we did do, which was new, was to introduce the stress energy tensor for fluids. T mu nu. It's a tensor, of course. It's a rho plus b. U mu nu plus p eta mu. Of course, I did not introduce it for nothing. This basically tells us everything, when we're talking about fluids rather than single particles, this tells us P is the pressure, rho is the energy density. This tells us essentially the flow of energy and stresses from between the different directions. Flow. And the conservation equation, energy and momentum, can be written in a very simple form. T mu nu comma mu is equal to 0. See, this gives rise to Euler's equation. If you have seen that in fluid dynamics, if you have taken a course in fluid dynamics, you'll recognize this is really the relativistic generalization of that. If you have not, it's a pity. But obviously we're going to use that.
Wait, what is relativistic about this?
What?
This is the relativistic generalization?
Yes, of course.
Why is what makes it different from the one we studied in Hydro?
But I don't believe you studied the relativistic velocities in hydro. All the
No.
velocities that you studied in hydros was classical.
We did express everything using tensors and Euler's equation. So.
Should have. Very good. So this is the relativistic Euler's equation.
Okay.
This is true also when the velocities are close to the spin of light.
Okay.
It's the point of special relativity. And of course, in the limit of velocities which are much smaller than the speed of light, it reduces back to the equations that you've seen previously. I don't know. Thank you. Okay, and then we moved on. We started to talk about this. Now it's recording. Okay. Then we started to talk about general relativity, and the starting point was the principle of equivalence. And the principle of equivalence between inertial mass and gravitational mass. And I said that technically there are two principles of equivalence. The first is called the weak equivalence principle, WEP, which is really Otvosh's experiment. Meaning Mi equal mg. And then the conceptual thing is called the strong equivalence principle, or the equivalence principle for short, says that in arbitrary gravitational field, in arbitrary gravitational field, it is possible to choose a locally inertial coordinate system such that within, of course, a sufficiently small region of the point in question, the laws of nature take the same form as in an accelerated coordinate system, Cartesian. For short, this simply tells us that wherever we are subject to any gravitational field of any kind, there is always a free-falling system. Right? So regardless, we are here. Now we're in the class, right? There is always a system of freely falling. And in that freely falling system, there is no gravity, locally. And again, the correct way of thinking of these things, think of an elevator. You are now in an elevator, very long elevator, and so you cannot see what happens outside, and the cable is being torn. And now the elevator is freely falling down. There's nothing to worry about. There is a safety measure. You're not going to be killed. But when you are falling down, when you're freely falling, you cannot measure gravity. Everything cancels out locally. Because of course, globally, if we have two physicists here, right, they will be seeing that they are attracted to each other, but that's of course because they're really attracted to the center of mass, which is the center of Earth in this specific case. And so, if this is long enough, they could measure to see that they are getting slightly closer to each other, so they could deduce that something happens. Yes?
What happens at the center of the Earth? I guess in general relativity it's solved, but in...
Nothing. There is no gravity. The same as Newtonian.
If you throw something, for example, there
Can
is
breathe.
a force acting on it towards the center.
Right now, it's a classical Newtonian. I did not speak about gravitational forces here. It will be a classical Newtonian. I mean, now we're feeling the force of what you're doing. Like you can take any body and look at it as if all the mass is concentrated at the center of mass. right? So we feel the same gravity as if we would feel if all the mass of the Earth was concentrated at that point. If somebody would dig a tunnel through Earth to the center, right? If you could do that, then of course, so this is Earth. When you're here, you're feeling gravity. When you're right here, you don't feel anything because gravity cancels from both sides. Right? But that's got nothing to do with what we're saying right now. Right? What we're talking now is conceptually the fact that when we are in a freely falling system, we cannot measure gravity at all, regardless of what is the source of gravity. This is the equivalence principle, which says that there is always, regardless of how complicated the gravitational field that we are, we can always find some freely falling coordinate system.
If it would be like a point mass with the mass of the Earth,
Yes.
then it would have a force enacting on an object that is slightly to some angle of it.
Doesn't matter. Again, it's local, right? That's what we're talking about local. Think of the gravitational field of the sun, right? From our point of view, the sun is so far that we can treat it as a point mass, right? But we are subject to the gravitational force of the sun. Of course, right? We're rotating around the sun. We're not just floating out in space. The entire Earth, including us. Right? The point is, regardless of where I am, I can always find a coordinate system which is freely falling. And in that freely falling coordinate system, I do not feel gravity locally. Globally, of course I do, because if I'm here, and Australia is somewhere here, right? Then my freely falling coordinate system would go in this direction, and the Australian freely falling coordinate system would go in that direction. So obviously we're not the same freely falling coordinate system. But this is a global effect, right? Today it's much easier to visualize that than 120 years ago when this was written. Think of free jump from an airplane, right? People do that for sports. Some people do it for sports, right? Then you don't feel for a few milliseconds or a few minutes. You don't feel gravity, while you do feel force friction from air, etc. The idea should be clear. There were other questions? That's clear. And then I said, okay, now so let's reverse the logic. Okay, so I reverse the logic. Now this is Earth, the surface of Earth, and this is our class. Right? I am standing right here, and you guys are sitting next to the desks, right? And we all feel gravity, right? And we know that we are on the surface of Earth because we can look out of the window and what we see matches what our intuition tells us we should see. But in principle, if we were, not on the surface of Earth, if we were now kidnapped by some aliens, right, all this class will be taken away, right? You shut the windows, again, think of it, you're in an elevator, right? And we are all inside the spaceship, and the Captain Kirk, of course, opens up the engine, so now there is no Earth, but there is just a spaceship. And the captain opens the engines of this spaceship such that the engines produce acceleration A, which is equal to G. Then what would we feel?
Exact same thing.
Exactly. We won't even know. There is nothing that we can say. Again, everything locally, of course, right? Everything locally. We could not tell that we would not feel any difference. Right? Nothing. We would feel exactly the same. That's the meaning of this equivalence principle. Right? And from that, we derive the first very simple but highly non-trivial result, which was called the gravitational redshift. What we said is that let's say that we are now in an accelerated system, inside an accelerated spaceship with some acceleration A, right? And there is some lead there. There is somebody here standing on the ladder. I call her Ayala, and there is Benny. And Ayala tries to signal Benny to tell him something. What she does, of course, is she sends him a photon. Let's use that color, photon A. And then after some time, she sends him a second photon. Sorry, that's called photon 1. And then she sends him a second photon, which is photon number 2. Then we show that because of this acceleration to a first order, we said that this is the height there of him is h. We said that the acceleration a is equal to g. And we show that delta tau Benny, this is Benny, this is Ayala. We show that the interval, the time interval difference between the proper time difference between the receiving of the two photons by Benny is not the same as the time interval as Ayala measured where she was sending the photons. And we show that to 0th order, delta tau Benny is delta tau Ayala times 1 minus GH over C squared. And this is a direct consequence of the fact that we have assumed that both of them are sitting in an accelerated frame. And because of the equivalence principle, we state that this is exactly what happens here on Earth. Now this is equivalent since the frequency of the photon, you think of a photon as this delta t is the time between two crests of a single photon, single signal, and the frequency is 1 over that. That means that nu of somebody is at infinity is 1 minus that, so it will be nu star 1 minus, well, this I can simply write as delta phi, so this is delta phi over c squared, or in a more precise way, this is nu star 1 minus gm over r c squared. And this is something which is measured. Because if we're looking, for example, at the sun emits light from its surface, or for that sake, any other star. It emits light from its surface, and reaching us. Now we are at infinity relative to the gravitational potential. This is right, this is gravitational potential. So the frequency we are seeing at infinity is less, meaning the light turns towards the red. That's the meaning. That's the name gravitational redshift. And this is something which we see. This is something which is very small. For the Earth is tiny. For the Sun is very small. For other stars, such as white dwarfs or neutron stars, which are more compact stars, compact objects, these are objects that you're supposed to learn about in, of course, in astronomy, astrophysics 101. Then the signal becomes more and more pronounced and gets up to tens of percent. But even though on Earth itself it's very small, it's non-negligible and is needed for this object that we today, all of us, have in our pockets, which is called GPS. Without making this correction, all our GPSs would stop operating properly within a matter of few hours. So you have a living proof in your pocket of the theory of relativity. Now, of course, this was tested experimentally. This was found in Rebka from the 1959 was the first measure of gravitational redshift. They were in Harvard. One of them just went on the top of the tallest building there. One was standing down below, and they just measured the frequency of, I think they used laser beams. They were very accurate enough, and no, in the 1950s it was already, technology matured such that they could actually measure. All right. Questions? Yes.
how can you capture these effects only by kinematics if it originally stems from a deeper, סיבה יותר מהותית, כאילו.
I'm not sure I understand your question.
You told us that it happens because space-time is curved and the photon travels not in a straight line. So how can we see this only from kinematics? If you understand.
I'm not totally sure I understand. I'm trying to make it as easy as possible. All right, I'm just showing you that once you accept that, this automatically follows. Right? At this point, I have not yet introduced the deeper level. I told you that there is, of course, a deeper level. But what I did, the calculation that I showed you just before the holiday about that, did not involve anything you have not seen before. It was a classical calculation. Of course, relativity is obvious, right? It will reproduce all the results that you all know from classical physics. Otherwise, it will be very embarrassing if everything that Newton have done turned out to be wrong. Only generalize them to regions which have not been explored by Newton. That is one of them. Right? So yes, I did that, and we're going to. You'll see. Basically, I think you will get the answer, because right now we just did the simplest thing, just to show you that once you accept that, from math and physics you already know. I did not have to introduce any new physics here. You automatically get a new effect that was not predicted in classical mechanics or classical physics. Right? So let's leave it like that. Of course, all the very fancy math we're going to do essentially will have observational consequences. Otherwise, there's no point in doing it unless you really like math. Yes.
How do the units work out in the gravitational potential equation? In the frequency shift equation, how does the units work out? Because it's 1 minus potential over c squared.
Mm-hmm. It's unitless.
Potential over c squared is unitless.
Take it out.
Okay, I'll take your up on that.
Check it out and you'll see the answer. This is the potential, Gm of R.
Potential doesn't have units in c squared.
Check it out.
Actually, it does.
Works. That is the reason why I still keep on c squared and I don't put it to 1. So I could have before already put it to 1. Right? Alright? Okay. So now, any further questions? Okay. Today we're going to do a lot of math and we're going to derive very important math results. Going back to your question, there is something which is indeed very deep here. We had 2 photons. They traveled exactly the same path in space-time. Right? Nothing changed. Right? I last signal 1 photon, she changed. Another photon, nothing changed. Yet, there was a difference in delta tau. This, when you think of it deeply, this suggests that the effect of gravity is to curve the space-time. Mainly that the space-time is not flat, Euclidean, but something happens to it. It's being curved, like a trampoline. What curves it is the energy. I said, how it's going to be curved, the mass rate. Right? This is gravity. Right? What we call gravity is a curvature of space-time. How this happens, I told you, it will take us several weeks before we can actually show that, because we require more mass. This will end up with what's called Einstein's field equation. Right now, I just want to see how to describe that mathematically. And that's what we're going to do now. A mathematical description of curved space-time. So again, the logic is that the gravitational redshift effect suggests, it doesn't prove it, but it suggests that in the presence of gravity, space-time is curved. Write it down. In the presence of gravity, space-time is curved. Well, of course. Lukuvi, yes. So right now we're simply taking this as a given, and then we'll prove that rigorously. Now we want to have a description of velocity, acceleration, like physical quantities in curved spacetime. What do we do? So, actually, it's not that difficult, but it's going to be a little bit confusing. We said that in every point in spacetime, there is always locally freely falling coordinate system, right? This one here. It's a locally freely falling coordinate system for this one here. Locally freely falling, meaning that within that coordinate system, which I'm going to call it psi, so there is always, we start from the starting point is that there is always a freely falling coordinate system, which I denoted exact not by x but by psi. Psi. Right? Psi alpha. In that coordinate system, special relativity holds. We set ours. Whole point. All the laws of special relativity. In that case, I can write down the proper time. D tau. Well, we've written it already. So d tau squared is a minus 1 over c squared. Eta alpha beta, psi alpha, psi beta. I just changed the names from x to psi. Didn't do it. Now, of course, this is a locally inertial, which means that assuming that there's no forces acting on the particle, then the trajectory of a free particle. Here it's important, I'm going to use capital U. So du alpha over d tau is d squared psi alpha over d tau squared, which is 0. Exactly the same thing that we did. Of course, u alpha. Again, I'm insisting on a capital U. Is d psi alpha over d tau. Questions? No? Now, I'm going to completely generalize things, and I'm going to write it down in any coordinate system. Note that what I do is completely general. I can have an accelerated coordinate system. I can even have a flat coordinate system, but written not in Cartesian coordinates, but in spherical coordinates. I can do what I want. I want to generalize, simply change coordinate system. So now we express the proper time. Express the proper time in arbitrary coordinate system. Which I'm going to call, of course, x here. Well, I can erase this part here. case yet. So what am I going to do? I'm going to use a chain rule, which you know very well, d tau squared. If I want to express it in terms of the new coordinates, I simply use the chain rule. So it's 1 minus 1 over c squared, eta alpha beta. And then I have d psi alpha over dx mu. Note the partial derivative here. Right? dx mu, d psi beta over dx mu, dx mu. Just use partial derivative to express the old freely falling coordinates with the new freely falling coordinates, which is minus 1 over c squared and g mu nu dx mu dx nu, where g mu nu is defined as eta alpha beta d psi alpha over dx mu d psi beta over dx mu. So this is actually, as the name implies, this is really what we call the metric tensor. Which is written in any arbitrary coordinate system, not necessarily a freely falling coordinate system.
And this is for coordinate transforms?
Yeah, I completely generalized. I said, okay, I don't want to limit myself now to a freely falling coordinate system in which there is no gravity.
Okay.
But again, it's completely general. It can still be a freely falling, but written, for example, rather than in terms of Cartesian coordinates, in terms of polar coordinates, spherical coordinates. Yes.
So I think mu can be any or
Any coordinates.
anything.
Completely. Any coordinates. I'm not limiting myself. Yes.
In the lecture notes, it says that d tau equals.
You don't have access to these lecture notes. What you're saying is the old ones.
Oh, it says here d psi alpha, d psi beta. And you wrote only psi alpha, psi beta. The first equation.
Which equation?
D tau squared.
Well, at alpha beta, psi alpha, psi beta. What's the problem?
No,
So it
just it says here d psi.
Oh, it's a
alpha.
d psi alpha. Of
Yes.
course. D psi. Sorry, of course. It's a d tau. Okay. Now, this new coordinate system, right, is completely arbitrary. I didn't specify what is x, so it can be anything. Right?
Oh, I have a question.
Yeah.
How can a coordinate system be a differential?
What's the problem?
The
The coordinate system is x, but d tau is a differential.
Okay.
So look at the difference of the coordinates. That's what matters.
Oh, okay.
Coordinate is a coordinate. I said this is a coordinate. Let's call it psi, and the new coordinate I call it x.
Mhm.
I'm looking at the d tau,
Okay.
right? That matters. Now, what about the freely falling? Right? We have a trajectory of a free particle. Right? So freely falling is like they don't have any forces. But what happens in this new coordinate system? Now the new coordinate system is general, right? It's not a freely falling. What happens to the freely falling? What happens to the trajectory?
You still have d
Well, that's-
squared.
That's,
That was the question.
that's it. I'm going to write it down.
Sorry.
We'll do this. So d u alpha over d tau is equal to 0, right? Trajectory of a freely falling particle. Well, again, u is d psi over d tau. I want to express it in the terms of the new coordinate system. So it's d over d tau. Now we have the psi over d tau. So I'm going to write it down as d psi alpha over dx mu, dx mu over d tau, because I want to express everything in terms of the new coordinates. So now I need to take the derivative of d over d tau of that. So again, I take first this part and then this part. So this is equal to the only thing I can do from here is take the second derivative of that and then d over d tau with respect to the new coordinate system. So that means that I have a d squared psi alpha dx mu times dx mu over d tau. That is for this part, and then this is just being copied, dx mu over d tau. Plus, from here I can take now the second part, so this is d psi alpha over dx mu times d squared x mu over d tau squared. Okay, now I'm expressing the old coordinates in terms of the new coordinates. Now, of course, I'm going to use the fact that I can have the inverse of that. So I have, it's a different color. So I have d psi alpha over dx mu times dx lambda over d psi alpha. What am I going to get here? This is a delta function, of course, delta lambda mu. So I can take that equation, again, this is equal to 0, and I multiply it by the inverse. So this is d x lambda over d psi alpha. So this and this goes down. So we have 0 is equal, I'm taking first this part, using the delta, so this gives me delta lambda mu, so I'm going to get a d squared x lambda over d tau squared. Plus, here I cannot do too much, it's a bit of a mess, so I'm going to write it as in terms of what's called a lambda, gamma, lambda mu nu. This is not a tensor. So I'm allowing myself, it has one upper index, two lower indexes, and go one on top of the other. Gamma lambda mu nu times what's written here, dx mu over d tau, dx nu over d tau, where gamma lambda mu is defined as, well, basically what we have here, dx lambda over d psi alpha, d squared psi alpha over dx mu dx mu. That's again is so important that it has its own name. It's called the affine connection. Which is an object. It's not a vector. It's not a tensor. It's simply this object that tells us how one coordinate system, the freely falling coordinate system, transforms into a non-freely falling coordinate system. And we're going to speak quite a lot about this object, but not at the moment. Right now, again, we ended up with this equation. This is the equation of motion of a freely falling particle. Right? It's the same equation, just written in new coordinates. So d squared x lambda over d tau squared, right, second derivative of the position, right? I can write it as the first derivative of the velocity, which is nothing but the acceleration, right? So I can write it down as d. Now I'm going to use a small u to differentiate. Du lambda over d tau is a minus gamma lambda u nu u nu u nu. Where now it's a small u, u nu is dx mu over d tau. Just put a note that will serve us for later. What we call as an affine connection is something which we're going to use to connect vectors which are located at different locations, different points along the manifold. That's why the name connection. We'll get to that down the line. Now, what did we get here before answering? So again, this is the same equation. This is the equation of a freely falling particle written in a different coordinate system. Now it's not a freely falling coordinate system. And what did we get? What is du lambda over d tau? Physically, what does it mean?
Oh,
Acceleration.
What? Acceleration. This is an acceleration.
So this is the acceleration that's inherent just from the coordinates.
So this is what we call, so when we're seeing a freely falling object, right, what we say is that it is accelerating. Right, because the entire coordinate system is accelerated in gravity. And this affine connection really tells us how it is being accelerated. Right?
So you don't have to invoke like forces, you just have to define the space-time like around,
Exactly.
around the point of gravity.
Exactly. General relativity, gravity is not a force. You have electric forces, magnetic forces, you don't have strong force, weak force. You don't have gravity is not a force. All right. This is but again, this is mathematically what we did. Something which is very simple. We just took special relativity, no gravitational field, right, moving in space, and then we just say, okay, now we're taking that and accelerating it. What is it accelerating? It's subject to some gravitational field. Right? Because of that, then the particle that we're talking about seems to be accelerated. But really, what is accelerated? Just a second. Really, what is accelerated is this is the effect of gravity, basically. It's the entire coordinate system. The freely falling coordinate system is accelerated. Exactly the same thing that we spoke about the example of gravitational redshift. The coordinate system of Ayala and of Benny were not the same relative to each other. They were accelerated relative to each other. So this is exactly the same thing that happens here. Question you had?
Yeah, so
Fine connection.
Yes. Is the presence of the field is has this set define if the law of the non field is present in the space.
Yes, but it's more general. I said this is true in any case where we're not using a Cartesian coordinate system. You can do the same for transferring any coordinate system because what we did here is completely general. I can look at the Euclidean space. I'm going to show it to you in a second, right? I'll give some example down the line. I can look at the simple Euclidean space, but just write it down in the Cartesian coordinate system. I'm allowed. I will still get this affine connection, essentially. I'll still get this acceleration part. You'll see. We'll work it out. Yes,
What did you mean when you said this allows us to connect to vectors from different positions?
we'll get there. We said, I think I mentioned that vectors belong to a point in the manifold, right?
Yes.
Because in general, the manifolds are going to be curved.
Yeah.
So that gives a question of how can you connect a vector that appears in one point to a vector that appears in another point, which is going to be crucial when you try to take something like a derivative of a vector. Cool. We'll get there. Okay, one step at a time. All right. Of course, what we did is true for a massive particle. I just kind of quickly go through. When we have a massless particle, such as photons, the calculation is, of course, the same, only that we cannot use now tau. Let's not erase that, because that's important for the time being. So, for massless particles, as we had before, we cannot use tau because tau is always 0. So instead of that, the tau, we use some other parameter, which you call whatever sigma, instead of the proper time tau. We use an arbitrary parameter along the word line, call it sigma, and then the equations get exactly the same form, right? D u alpha over d sigma d squared psi alpha over d sigma squared is equal to 0, and then the equation of motion would be 0 or minus g mu dx mu over d sigma dx mu over sigma. That's the same equation of motion, or and d squared x lambda over d sigma squared plus gamma lambda mu dx mu over d sigma dx mu over d sigma. Now, these equations, they're so important that they get their own name. It's essentially the same equation, right? This. So this has a name. These are called the geodesic equations.
So these describe the shortest path in the curved space.
Exactly. These describe, this is a generalization of a straight line. Because a freely falling particle is just moving in a straight line, right? Geodesic equations, and actually we're going to prove it. I was hoping to prove it today, but I'm saying that I'm not sure we'll make it today, so Max will do it in the next lecture. They describe how shortest path in any arbitrary coordinate system. Yes?
Just to make sure, besides the reparametrization from lambda to sigma, it's from tau to sigma, it's the exact same equation.
Yeah, the equation looks
Okay.
the same. Okay. Before we move on to the proof, then there is something, it's a little bit more math, and that's about this affine connection. Right? So I wrote it down as a parameterization of the new coordinate system x in terms of the old coordinate system psi. Right? So the only thing we did really, right, is mathematical manipulation. Just change of coordinates. This is something completely mathematical. There is no physics in it. Right? But then we did give it a physical interpretation. Right? We said this is the accelerations we're seeing. This is a physical interpretation. This is a completely mathematical. This is mathematical, right? But the interpretation is this is the acceleration due to gravitational force, essentially. That's what it is. So this part is, write it down, acceleration due to gravitational force. But again, this is our interpretation. Going to be the right one, of course. Which means that in some basic way, this is going to be representing the gravitational force that we know and love. Now, the proper time interval, tau, right, is determined by the new metric tensor, G mu nu. Because simply we change coordinates. So there must be some sort of a connection between G mu nu and the fine connection. They need to somehow be related to each other if this interpretation is to be correct. Right? And in fact they are, but in a non-trivial way. What I'm going to prove to you now is the connection between the new metric tensor and the affine connection. And what I'm going to show you is that this is going to be related to the metric tensor and to the first derivative of the metric tensor. Which when you think of it deeply, that means that if this is a affine connection related to the gravitational force, then the first derivative of the force is a what?
Momentum? No.
Question in general physics. What do we call a derivative of force? Potential. Potential, right? So that means that G, the interpretation of G actually is going to be much deeper. It's going to be associated with the gravitational potential. One step at a time. So right now, let's do that. Okay, so I'm going to erase that. Actually, the G mu nu, maybe I should write it here because what is it? G mu nu at alpha beta psi alpha over the x mu d psi beta over d x mu. Fine connection gamma lambda mu nu is x lambda over d psi alpha d squared psi alpha over dx mu dx. Okay, so what I'm going to do now is the relation between the metric tensor and the affine connection. Yes?
I'm a little bit confused. G mu nu can be any metric?
Yes, it's defined by the coordinate. I said the coordinates that I select are completely arbitrary.
Okay. And the eta alpha beta is still Minkowski.
Yeah, I define. Whatever I define, I'm not touching.
So we define any
We started by looking at the Minkowski space. We defined coordinates, Cartesian coordinates in Minkowski space, the same one that we love to use. Now what we're doing is we're looking at any arbitrary coordinate system, x.
all of them defined by the Minkowski.
I just say I want to have any coordinate system that I want to be able to describe any gravity, any curve, any space-time.
No, yeah, but
It can be a flat space-time. Minkowski is a flat space-time.
no, I mean we can define any metric by using Minkowski metric, like it says.
Yes. This is the definition. The matrix eta is the same matrix eta. I'm not going to touch. Once I define it, it's there. It's not going to be. I'm not going to touch it from here until the end of the semester. G mu nu, of course, that depends on the problem at hand. Right? Which coordinates you're going to use? You have different metrics. Okay, so how do we do that? Well, we start with the definition of G here. And I'm going to take the derivative of that with respect to x lambda. So dg mu nu over dx lambda. What do I do? Right. Eta is just a matrix, so I don't touch it. So it's just d squared
psi alpha over dx lambda dx mu, d psi beta over dx nu eta alpha beta, right, plus now the second derivative term d psi alpha over dx mu, d squared psi beta over dx nu dx lambda eta alpha beta. Okay. Now from the definition of the affine connection from here, we can multiply that by the inverse. So d psi alpha over dx lambda. So we have d squared psi alpha over dx mu dx nu is gamma lambda mu nu d psi alpha over dx lambda. Okay, I mean formally I just multiplied by the inverse and then take a delta function, but then the answer is quite clear. So what I have is from here dg u nu over dx lambda. I can write it as like this one, lambda, so alpha lambda mu. So instead of mu nu here, I should put a lambda mu. Right? Because mu here. There's a lambda mu here, so this will be a lambda. So instead of lambda, let me write this as a rho. If you notice, this is a dummy index, so nobody cares really. So I have what did I do? So I have here gamma rho lambda mu d psi alpha dx rho, and whatever is left from here, d psi beta over dx mu eta alpha beta. Sometimes in this course we have to go through this math. It can be a little bit annoying or confusing, but it's just algebra, so you just have to follow very, very closely. Now we do the same thing from here. All right, so instead of alpha, we have a beta here. So we have a plus this part here would be a gamma rho lambda nu d psi alpha over dx mu d psi beta over dx rho eta alpha beta. Here this goes with whatever we have here, right? We just change alpha to a beta. We just dummy indexes and everything works out fine. So what is written here? This is just G. Right? So this is gamma rho lambda mu G rho nu. And here this is plus gamma rho lambda nu. This from here, right, it's just G mu rho. Rho mu, as you can see, G is symmetric here. Let's switch it to rho. Okay, algebra, annoying, but still just algebra. So what I do now, I just take this equation and I add the same equation with mu and lambda exchanged, and subtract the same equation with nu and lambda exchanged. Then what we get is the following: dg mu nu over dx lambda plus dg lambda nu over dx mu minus dg mu lambda over dx mu. What do we have? So they change again. These are dummy indices, so I just switch it into kappa. I'm allowed to do that. It's on the index. So you have gamma kappa lambda mu g kappa mu plus gamma kappa lambda mu g kappa mu. Now I have the same thing with mu and lambda exchanged. So plus gamma kappa. And mu and lambda exchange, you can see here from symmetry that it doesn't matter anything. If I change the lower two terms in the affine connection, because of symmetry, it doesn't matter, it's the same thing. So it's gamma kappa lambda mu g kappa nu plus gamma kappa mu mu g kappa lambda, right? Exchange mu and lambda, and then minus exchange of mu and lambda. So I have a minus gamma kappa nu mu g kappa lambda minus gamma kappa lambda nu g kappa mu. It looks scary, but it's just algebra. Just making sure you have to follow very closely all the indices and you don't get lost with them.
Why do we add and subtract those coordinates?
Because now there is a magic. Because this term cancels with this term. And this term cancels with this term. And what we are left, this is twice gamma kappa lambda mu g kappa nu. Right. Now we basically define the inverse of the metric. We define, of course, with two upper indices, g mu such that g mu sigma g mu kappa is a delta sigma kappa. That is the definition of the inverse metric. And then we take this equation here and we just multiply both sides by the half of the inverse metric. So we multiply that by half g mu sigma. So we have a delta here, kappa sigma, so kappa here becomes a sigma. Then we end up with a gamma sigma lambda mu is 1/2 g mu sigma times whatever is written here, d g mu nu over dx lambda plus d g lambda nu over dx mu minus dg mu lambda over dx, which is essentially what I promised you. I express the affine connection in terms of the metric and its first derivative, but it turns out to be way more complicated than you may imagine. So I have the metric. From the metric, I calculate the inverse of the metric. And then I take the derivative with respect to the new coordinates, which enables me to calculate the affine connection. Now, written in this form, the affine connection has a second name. So important, it has two names. This is also called Christoffel symbol. Symbol. And another way of writing it is with curly brackets. Sigma lambda mu. If you see something that's written like sigma lambda mu, you also see it. In terms of affine connection, this is more in use various aspects of differential geometry. In this course, we will make less use of this notation. So you should know that this exists.
Well, what is this essentially?
Well, I told you, essentially this will tell you how much the space-time is curved in a way. Let me do an example. So I'm going to take a very simple example. Right, so a simple example, just to show you, I mean, okay, the first time you see that it looked like horrible, right? But after a while you get used to it, so okay, actually it does make sense. I strongly urge you to do that at home. I'll give you homework so that you can practice that. Now I told you, let's look at the flat metric. I'm not going to touch the metric. Example. 2D Euclidean space. Written in spherical, in polar coordinates. Oh, okay. What is an element of length in these coordinates? Ds squared. Written in r theta.
dx mu dx nu, right? G mu nu dx mu dx.
Of course, this is G mu nu. Dx and dr d theta. What is you know that, what? It's dr squared
Yes.
plus
R squared d theta squared.
dr squared plus r squared d theta squared. Right. So from here only, you don't need to do anything else. What is G mu nu? What is it? Write matrix G mu nu.
So the eta's 1
1
0 0
R square.
Right. What's the inverse?
1 0 0 1 over r square.
Now you want to calculate the affine connection. Right. So now you need to start taking the derivative. It's written here, right? But the only coordinate in which the derivative makes any sense, right, is dg22 over dr, right? Instead of the x lambda dx mu, this is the r d theta. So the only thing that you get when non-zero is dg over dg22, right, over dxr, whatever you call it. Do the calculation at home. I definitely do that at home. You find out that gamma r theta theta is minus r. Gamma theta r theta is gamma theta theta r. These are always symmetric in the last two indexes. Is 1 over r. To be continued. But you can definitely do that. Yes.
Is there an intuition for Christopher symbol lambda UV?
Not for now. For now, I want you to get the intuition for what is G mu nu. Sorry, it's the inverse. For what is G mu nu. This tells you how to describe a line element.
Yeah. Makes sense.
How to describe a line element in any coordinate system. This is a simple flat space-time. I think I give it to you as homework, if not just do it for yourself. What happens if in flat space-time two-dimensional sphere, surface of the Earth, then there is no r, r is constant, just theta and phi. Do that. I think you have it in homework. Yes.
So I thought here evaluation in flat space that we call for it's no one of the entry. Nothing
right now, this is flat space.
Yes.
This is a flat space. I just show you. Remember what we did. All this calculation. Okay. I want to be very sharp on it, right? We did a mathematical manipulation of coordinates, which was completely general. Okay. And then we started to give it some sort of we started to give it some physical interpretation. As far as the mathematical, this is a mathematical manipulation. I just changed coordinate. I can do that. What you'll see if you try to calculate the forces here, well, you will get some force here, but you have to think what it means. Right now, what I want to do, I do want to strengthen up the whole point here. Actually, still need to strengthen the mathematical formalism here, and that is we need to take another at least 15 minutes because of the mess at the beginning. What I want to do now is to talk about the geodesic equation, which I have not written here. Right? I have written it, but I erased it. So the geodesic equation d squared x rho over d lambda squared is minus alpha beta dx alpha d lambda tau. Now I argue that this is not just an equation, another equation. This equation describes a free falling particle, and really this is the generalization of the idea of a straight line to curved spaces. So I'm going to prove it to you right now. I want to show you that we get the geodesic equation from the variational principle. Now everybody here took analytical mechanics course. Yeah? Is there anybody who did not take it? You're all familiar with Lagrangian formalism. So we're going to do it right now. I'm going to use the Euler-Lagrange equation to prove to you that the geodesic equation really gives you the shortest path between 2 points. Right? So let's see how we're going to do that. The geodesic equation and the variational principle. So there are two points to emphasize again. First is that when we say free particle, right? In Newtonian mechanics, that means that there are no forces acting on it, including gravitational force. In GR, it can still be free if there is a gravitational force, because gravity is not a force. Okay? So free particle, it can be subject to a gravitational force, and we still call it free. Okay? That means free. The second thing is that a free particle in GR, gravitational force is not included. And the second is that geodesic means shortest path. In the sense that, what does it mean shortest path? In the sense that the path taken by a particle moving from point A to B minimize, or really extremize. What? What does it minimize?
You need some form of action, right? Or like,
What is it minimizing?
wait, time.
Time. What time?
The travel time.
Proper time. The proper time. Minimize the proper time. Right. That's the meaning of the shortest path. So yeah, I mean, basically this is generalization of a straight line. Okay, concept of the straight line. Okay, so we're gonna do it twice. So we start with a special relativistic treatment because it's slightly, marginally easier. So one is a special relativity. We don't need to worry about any curvature. We said that the path that maximizes, that minimizes the proper time. What is the proper time? From A to B is integral from A to B along the path of d tau. Right. What is d tau? Well, you can select the parameter. Right, so this is integral. I'll call it d lambda because I don't like to use d tau prime. So it's we had a minus 1 over c squared, which I should take to unity, but doesn't matter. Eta alpha beta d psi alpha over d lambda d psi beta over d lambda to the power 1. Right. That's the proper time it takes a particle as it travels from A to B along some path specified by lambda. Right. So lambda, this is a parameter along the word line of the particle. So, how do we calculate that? As you did in Lagrangian mechanics, we use the variational principle. We slightly change the path and look for the minimum. So really here the integral is playing the role of the Lagrangian, and psi is the dynamical variable, and lambda, d lambda will be the time. So the Euler-Lagrange equation minus d over d lambda of dl over d psi alpha over d lambda plus dl over d psi alpha is equal to 0. This is Euler-Lagrange. This is basically the Lagrangian, yeah. So what is the L d psi? How is the path depend on the xi?
What do you mean?
Hmm?
What do you mean?
This, what is the L d psi? No, you're not really.
It doesn't, no, it depends on the derivative.
It does not, right? It just depends on derivative, right? So this is just a 0. Nothing to do with the side. So the equation of motion that we have, dl over d psi alpha over d lambda. So we have a d over d lambda. I don't need the minus here, it's a 0. Basically, this is the power 1/2, right? So I have 1 over 2l times a minus 1 over c squared. And then because they are symmetric, then I have a factor of 2 here. Eta, whatever I'll call it, sigma beta, dxi beta over d lambda.
Wait a sec.
Yeah.
The thing you marked L, shouldn't it include the squared 1/2 as well?
Yes. L is minus 1 over c squared. Eta alpha beta dxi alpha over d lambda dxi beta over d lambda to the power 1/2. That's fine.
dl over d psi lambda, right? It's 1/2 over L times whatever we have here. 2 here is because of the symmetry. Right. Now L is also d tau over d lambda. Here. Here. Yeah, so this is the L here is d tau over d lambda. So I have d over d lambda of essentially what we have here is d psi sigma over d tau. Forget about the 2 and 2, the c squared and c squared, so I'm just left with d psi sigma over d tau. So what is left is just to multiply by d lambda over d tau, and we end up with a d squared psi sigma over d tau squared is equal to 0, which is of course the equation of motion, fairly funny particle in special relativity. Not surprising at all. Alright? Now let's repeat the same thing exactly, but now doing in general relativity. Right, again, this is the equation of motion. Equation of motion of a free particle in special relativity. Now let's do exactly the same thing, but with in general relativity. And I told you the calculation is going to be marginally more complicated. Does anybody has any question? So 2 general relativity. So tau, of course now we're going to write down g alpha beta dx alpha dx beta L is minus 1 over c squared g alpha beta dx alpha dx beta. This is the Lagrange equation of motion. So now let's remove that. What do we have now? D over d lambda of 1 over 2L minus 1 over c squared 2g sigma beta dx beta over d lambda. But now we have this extra term. I just move that to the other side, right? So I have a plus here. So this is equal. What is dl over dx alpha? Now L does depend on x alpha.
Yeah.
Not only its derivative because of the metric. Exactly, right? Because the metric itself depends on x alpha, which is not written here specifically, but it doesn't matter. So this is again minus 1 over c squared, 1 over 2L, and now we have dg alpha beta over dx alpha. Sorry, dx. What do we do here? Dx sigma. So of course, let's use the same. And then dx alpha over d lambda, dx beta over d lambda. So from here, as I had previously, I end up with a d over d tau, g sigma beta, dx beta over d tau. And from here I have 1/2 that is removed is the other one, dg alpha beta over dx sigma dx alpha over d tau dx beta over d tau. Of course, we multiplied everything by the lambda over d tau. So overall, now I'm going to expand that. Let's take it here. So I don't need to erase it. So I can expand that to write down this. I'm going to open. So this will give me dg sigma beta over dx mu dx mu over d tau dx beta over d tau plus g sigma beta d squared x beta over d tau. Right? We just expanded these two. Then now just add that. So minus sign, minus half g dg alpha beta dx sigma dx alpha over d tau dx beta over d tau is equal to 0. That already looks quite close to the geodesic equation. Maybe you don't see it right away, but now it's just a matter of reshuffling some of the indices. Let's see. Start with that point. So g sigma beta d squared x beta over d tau plus this I can write as 1/2 change the indices here. So we can change this dummy index to alpha. So dx alpha over d tau, dx beta over d tau. Here I have dg sigma beta dg sigma beta over dx alpha. Now I can also shuffle with these indices here. So I can write it down plus dg alpha sigma over dx beta minus what I have here, minus dg alpha beta over dx sigma dx alpha over d tau dx beta over d tau is equal to 0. Then what is left is just to multiply by the inverse metric, g sigma rho, to end up with d squared x rho over d tau squared plus gamma rho alpha beta dx alpha over d tau dx beta over d tau is equal to 0. Which is exactly the same geodesic equation we got before. What was the point in doing that? The point was to show you that the geodesic equation goes way more general than the use we're going to make in GR. For example, if you're considering how many of you ever flew to the US, North America? Now you know that when you fly, you have this, and many of these today's airplanes, you have this small map, right? That shows you where you are on the flight route, right? So if I'm having this, so this is a small map, right? Then this would be America, whatever, right? This is Greenland. This is Europe. Mediterranean. We are somewhere here. This is Italy. Right, whatever. Right. How does the route look like? Yeah.
Because it's a
It
curve.
goes like that. Why does it go like that?
The Earth is round, so
Why is it going? Typically, if you fly from here to New York, it will take you over Greenland.
They flatten the map, so you can look at like.
Right. What does this curve really represent?
Straight line on the
This
surface.
is a straight line on a curved surface, right? The airplane is subject to the surface of the Earth, right? This is the Earth. Right? I haven't forgot to bring it here, but I'll try to bring it to remember. Hopefully we can meet again in person and I hope I will not forget. Then the shortest path between, let's say, Tel Aviv and New York takes you through Greenland. Now, it's not that the pilot wishes to show you around the world and enjoy the view. What they really want, of course, is to save fuel. So, minus some political constraints, mainly due to safety constraints, airplanes will always take you through the shortest path from point to point. But of course, the shortest path is subject to being attached to the surface of the Earth. So if you take the surface of the Earth as a two-dimensional sphere, surface, right, two-dimensional sphere, then this exactly will represent the shortest path. This is the equation that I don't know if they naturally know how to solve, but this is exactly the equation that we have. Now, before we move on, I'll just say, okay, I can just write it down. And what we just did right now was just to prove you that this is indeed the shortest path, regardless of which problem you're thinking of. Right? Of course, this I can write down as du rho over d tau. Plus gamma rho alpha beta u alpha u beta equal to 0. Of course, as a final comment, if I'm looking for photons, then again I will do the same. The equation will look the same, but I cannot use tau. I have to specify some other parameter along the photons world line, which you can call whatever Greek letter you wish, sigma, lambda, whatever, and just write it down here. Right, so for massless particles, we have the geodesic equation. For non-geodesics, that's how it's called, non-geodesics. And again, it looks exactly the same. D squared x rho over d lambda squared is minus gamma rho alpha beta dx alpha over d lambda dx beta over d lambda. Of course, lambda is a parameter along the world line of the photon or any other massless particle. It's called the null geodesic equation for null geodesics. All right, I think we exhausted our time. There is still some more things that I want to tell you, which may hopefully get things a little bit more clear in your head. Now, can I have a look at what you filled in? You did not fill it in yet. Oh, there's nothing much left here, honestly.
יום ראשון זה שעתיים.
What?
Yeah, Tuesday.
This would be problematic from my perspective, but is there anybody here that is not have?
רגע, ביום ראשון אין שעתיים פנויות? היה רק שני.
Guys, I'm asking you, is there anybody that has any lecture on Tuesday between 12 to 2? Anybody in this classroom? Okay, I mark it to myself. I don't know yet, but I may be doing something with that.
could cause me some problems because I'm not necessarily free, but we'll see. And then all other things here are built. All right. Any further questions before we go?
רק מעדכן שבזמן ההרצאה הזאת תתקנו את כל המבחנים של שבוע הבא, באפליקציה שלך.
לא שמעתי.